Hello stats fans, and welcome to section 2.1 where we talk about histograms and related topics. Let's start off by talking about what a histogram is. It's a graph that's going to allow us to make sense of some data, but we could define it this way. A histogram is a graphical representation of the distribution of data. So if we have a pile of numbers, it's hard to make sense out of this pile of numbers. What's the average number? What's a typical number? How spread out are the numbers? It's just a bunch of numbers. So what a histogram is, it's a picture of the data. And with a histogram, we can see how spread out the data are, if they seem to be bimodal, if they're clumped together, if it's more like a bell-shaped curve. So the histogram, we can get a pretty good idea of how the data are distributed just by looking at the picture. So we've got a couple pictures here coming up, which are histograms. But first, what I want to do is look at this, where this came from. These histograms came from page 57, number 16, which is essentially just a pile of 70 numbers, and they represent the glucose blood levels in milligrams per 100 milliliters after a 12-hour fast for a random sample of 70 women. So let me show you what these numbers look like. So here they are, 70 numbers. And when you just look at 70 numbers, it's hard to make much sense out of the data. So what we're going to do is I'm going to show you a couple examples, one using Excel and one using Minitab, where the software took these 70 numbers and turned them into a histogram. Now just to note, if you look at the numbers here, we can see some of these have been marked. The smallest number is 45. It occurs a couple of times. There's a 46 over here. The largest number is 109. And sometimes this is taught, you learn how to make a histogram by hand, but it really is fairly time consuming, and nobody really does these by hand, especially considering that most data sets are far larger than 70 data points. So if you look at this first histogram, this is from Excel. And Excel doesn't do a real great job with a number line. This is not really ideal here. Normally just want to have a regular number line, and you want to have these numbers here, the endpoints, marked off. I mean, they sort of do here. It's just not ideal. So it would be like you'd have a number line with 45, 56, 67, 78, 89, 100, and 111. Now sometimes also, especially when you're not in a stats class, but in marketing, when you see an advertisement, then a lot of times they'll use just the midpoint. They'll put the midpoints in here. It's just a little easier to read, a little nicer on the eyes. And then here's how we read this. So we've got a frequency here, and this is actually a 3. So what that means is in this pile of numbers that we had, the 70 numbers here, 3 numbers are between 45 and 56. And since sometimes these are not real easy to see, so I'm just going to write the numbers up here. 27, 7, and 3. And the way Excel splits these up, we have what's called these classes. These are each a class of numbers. And we've got we always want to label the axis. So we've got a label here. We've got a label on the horizontal axis. We've got a label on the vertical axis. We've got a title. We always want to have that. We want to make it really clear when we produce a histogram, or really any graph. We want to make it so that it'd be difficult to misread it. So we want to have a title every time. This up here is the title, tells what we're looking at. This is a frequency. And histograms sometimes are called frequency histograms because it shows the frequency. And then we've got a label here. We've got a number line here. Again, not an ideal number line. But this is saying this 8. You can read it right here, 8. There are 8 numbers in this set of numbers that are between 56 and 67. There's 8 of them. So there's 22 numbers in this data set between 67 and 78. And 27 here, 7 here, and 3 here. So if you add all these numbers up, we should get 70, because there's a total of 70 numbers in this data set. So it's good to look at Excel, because Excel is everywhere. I mean, a lot of you will end up using Excel And this is the way an Excel histogram looks. Then we've also got another one down here. This is from Minitab, and it shows the same information, but Minitab calculated the classes a little differently. This is how our author tends to do it. So our author tends to, if we have whole numbers, tends to make these end up with decimal points by 0.5s, because that way, if you have a data point, it'll never be on the line. So when you do this, when you make these end up ending with a 0.5, then no data sets or no data points will end up right on the line. But other than that, it's very similar. You have the horizontal axis, which is labeled. These look a little nicer here because the numbers are lined up where it's easy to make sense of it. You've got a title here. The vertical axis is labeled. And they've just figured out the classes a little differently. You can see 45 to 56. This is 44.5 to 55.5. So they differ a little bit. So the way that Minitab figures this out is we have 3, 7, 22, 26, 9, and 3. So again, what this means is in that set of 70 numbers, 3 of those numbers are between 99.5 and 110.5. And these just vary a little bit just because you're using different software, and normally you can tweak these however you need to tweak them. One thing also, our book will often, although it teaches it this way, it teaches us to do this, but often our book will use midpoints. So our book won't use these numbers here. Our book instead would do something like this. It'll have a midpoint here of 50, a midpoint of 61, so it's a point right in the middle, 72, 83, 94, and 105. So each of these numbers, like 50 is right in the middle of these two, 44.5 and 55.5. So you add these numbers up and divide by 2, you get 50. So sometimes the book won't have these endpoints here. They'll use midpoints instead. And that's typically actually how you see it when you actually see a histogram in an ad or in the news. A lot of times it just seems like it looks a little neater with the midpoints. So for us, we just have to be able to read these. We need to be able to look at a histogram and make sense of it. Another graph that we'll see in this section is called an ogive. Now honestly, I don't really hear it called ogive very often, but our author uses that term. Usually I'll hear it called a cumulative frequency curve. But what this is a graph that displays cumulative frequencies. And as I mentioned, it's also called a cumulative frequency curve. So this picture here is from the same data set. It's from page 57, number 16. And the way this works, so this is an ogive. It's still for the glucose blood levels. And you notice I'm using Minitab's way of dividing these classes. And remember, class is just a set of numbers here. So there's 1, 2, 3, 4, 5, 6 classes, 6 sets of numbers. So you've got the same horizontal axis as last time, the vertical axis is frequency, but now we have to go up to at least 70. So we just want to go, if we need to display 70 out here, we want to go to at least 70 here. So this one goes to 80. And here's how you read this. Basically, it's cumulative frequency. So what this ogive is saying is that between 44.5 and 55.5, you pick up 3 numbers. There's 3 numbers between here and here. Now, if you look on the previous graph, you'll see that between 55.5 and 66.5, you pick up 7 more data points. So this 10 is from taking a 3 and adding 7. So it's from this 7 right here, right? So we had 3, we added 7, so that's going to give us 10. And then for the ogive, next time what we're going to do is add another 22. Add this 22. And then you can see the 22 gets gets added with a 10, so we get to 32. So what this is saying, the way you read an ogive is you're saying below 77.5, we have 32 data points. There's 32 numbers in that pile of 70 numbers that are less than 77.5. So you just keep adding. So if you look on the last page again, between 77.5 and 88.5, there were 26 data points. So I had 32 that were less than this. Now I add another 26, right? 32 plus 26 gives us 58. So this just means that if you look at this number, 88.5, 58 of those numbers are less than 88.5 milligrams per 100 milliliters. And then the next class from here to here, we have 9 data points, so we add on 9 more. And then finally, the last class, we had 3 numbers that were between 99.5 and 110.5. So you add those 3 and you get to 70. So at this point, all 70 numbers are less than 110.5. And the nice thing about math or statistics is that we need to be able to make sense out of this data, even if we have no knowledge of glucose. So some of you are probably in the health field, and so you may have some intuition about this, like maybe this number to you is a very high number because you're in that field, and that's great. And if you're not in that field, it's okay. We still have to be able to read this. So with math and statistics, you can read data from any field, right? Even if you have no intuition about this. Like I didn't study healthcare. I don't really know much about this data set. I don't know how common these numbers are or if any of them are real unusual, but I know how to read the data. And that's what we have to be able to do throughout this course. We're going to see data from fields that you just don't know anything about, and it's okay. We still have to be able to read the data, though. That's why we need this. We need to, whenever we make one of these graphs, we need to label the axis, the horizontal axis, the vertical axis. We need a title so that anybody can look at this graph, and if they understand what an ogive is, they can read this data set. Okay, example 4, I've got a question here. How many patients have a glucose blood level less than 88.5 milligrams per 100 milliliters? Well, we look at the ogive here. Here's 88.5. We look up here, 58. So there are 58 patients who have a glucose blood level less than 88.5 milligrams per 100 milliliters. So there are a few different shapes of histograms. I'll draw these here, but if you want to see better pictures, they're on page 49 of your book, or in the ebook, just they're in this section. Also, in section 3.1, we'll look at these same shapes again, but we'll look at them with more detail and talk about like where they may occur. So the first one here is mound-shaped symmetric. This will end up being really important for us in chapter 6, but this is a fairly common shape for a histogram. So if you have, let's say, a horizontal axis, and then a mound-shaped and a mound-shaped symmetric histogram will look something like this. So the name is pretty good. It's a mound-shaped symmetric histogram. And you can see it right in here. So these are the classes, and it won't necessarily be as perfect as this. So a lot of times these histograms will be like kind of mound-shaped symmetric. So it won't be quite this perfect, but the general overall shape would be something like this. The next one that we'll see is what's called a uniform or rectangular. So I'll make the horizontal axis. And this one is kind of a very boring distribution. So we'll see these. We'll see like a probability distribution for rolling a fair 6-sided die. The probability of getting a 1 or a 2 or a 3 or whatever is all the same. So that's this. It's a uniform or rectangular. Both these names make sense. So each of these classes of numbers have the same frequency. So it just looks like this. This one we're not going to do a whole lot with in this class. Another one that we won't see a lot, but it'll come up occasionally, is bimodal. And basically what this is there's going to be a histogram that has a couple of peaks, distinct peaks. So they have to be separated by at least one class of numbers. So sometimes you'll see a bimodal graph. If you do heights of humans and you combine men and women, you'll get typically get two modes. You get a mode where the say the average male's height is, and then you get another one the average female's height is. But they look like this: bimodal, bi meaning two modes. They have these two peaks, and depending on how you define this, is not agreed upon. Sometimes they have to be the same. Sometimes this one could be taller, but it's still like two peaks. So it won't matter to us. We'll just have to be aware that bimodal just means there's these two peaks, and we really won't see too much of those. Now the next two we'll see quite a bit: skewed left and skewed right. And as I mentioned in chapter 3, we'll talk about what kind of data sets tend to be skewed left or skewed right. So for skewed left, if you look at the picture, it looks like there's a tail to the left. So skewed left, think of that as a tail on the left. A tail on the left. So we say the data are skewed left. So what do you think skewed right's going to look like if I make a histogram skewed right? Any ideas? You can probably make a prediction. It's basically a reflection of this graph. So skewed right, it just means it looks like there's a tail on the right. So remember, this horizontal axis is a number line. They're all number lines on these histograms. These are number lines. So it just means that as the numbers go up, there's still classes here, but the frequencies come down, right, as you go to the right. It's skewed right. And again, what that means, you can think of it, you can remember skewed right means there's a so-called tail on the right. All right, moving along here, we've got a definition. And we're going to start off with a definition that's not that great, but when we learn more about statistics, we're going to improve this definition a little bit. But this is for the word outlier. Outliers are just data values that are very different from other measurements in the data set. This is not a great definition, because what do you mean by very different, right? So we're going to come up with a better definition later when we have some more tools. But for now, we'll just think of this as more of like just a general idea that if you have a set of data and you've got some numbers that seem to stand out, for now we'll call those outliers. And the note here is that these may or may not be errors in the data. These outliers may or may not be errors in the data. So if you notice, if you're working with some data and you notice one of the numbers is really small or really big and it tends to stand out, well, you may have to check it out and see, was this a legitimate, just unusual data point, or was there a mistake made? As an example, let's say you are working in the registrar's office as a student employee making the big bucks, and let's say you're looking at some ages of students. Maybe there's some sort of financial aid requirement that they're working on. And so let's say you're just looking at a bunch of ages of students as they come in, and you see these numbers. So what about these numbers? See anything that stands out here? Remember, these are student ages. And you're looking around here, and you probably say, well, this one's a little big. And this one's definitely a little small if this is a college student, right? So then you have to look into it. So there is, just as an example, there is a student in the math department who's been taking classes here since the 1970s. He's been in a few of my classes over the years, and I don't know how old he is, but he's probably around here, I would say, maybe a little older. But so in this case, maybe you're looking and it's that student. You're like, okay, this is legitimate data. But this one, 4, is definitely in error. Okay, we get probably the youngest students that come to GRCC, they go to the math department, because we'll get some of those kids that just burn through all the math classes in their high school. They take calculus. I had a student in my calc class, and he was also a stats student. Him and his brother also, both very young. But this particular student was 15, really a serious student, very, very good at math. And he ended up doing a math seminar for us on Rubik's Cubes, but not only Rubik's Cube. He had Rubik's Cubes. He had a 30-some all twisting puzzles, and he could solve all of them very quickly. And he had to get a ride there from his mom because he was too young to drive. So we have young students in the math department, but 4, that's just not going to happen. This is definitely a mistake. Maybe it's 24, maybe it's 40, but this one you'd have to look into. But for now, we're just going to count any data value that tends to stand out. It's an outlier. We're going to tighten up that definition later on, but that's what we'll go with for now. Another type of graph we need to be able to read is a dot plot. So dot plots are good for small data sets, less than or equal to, I'd say, probably 40 or so. It's not written in stone, but 40 or so data points. Sometimes used in marketing reports. And they're quite often used in medical literature. So this is a dot plot that was made by Minitab. Excel doesn't support dot plots, which is sort of surprising because Excel does a lot for a sort of a general purpose spreadsheet. It has a lot of graphing capabilities and just general ways to work with data. But this one was done in Minitab. So I'll tell you a little bit about some of this software. So there's Minitab, and let's see, there's SAS, there's SPSS, there's R. These are the ones you'll see quite a bit. Minitab you see a lot of times at teaching school. It's a pretty powerful statistical software package, but it's not real expensive and it's very user-friendly. It's definitely the easiest to use of these. And all of these do a lot more than Excel. So there's Minitab. SAS and SPSS are also very popular. They're very expensive. They're not real user-friendly. So if you go to a teaching school, GRCC, Grand Valley, teaching schools tend to have Minitab. And then in some of the classes, so there's classes at GRCC and Grand Valley that use SAS. SPSS you see a lot of times in psychology. I think the psychology department here at GRCC uses SPSS. But these last 3 are a little trickier. They're really powerful, probably more powerful than Minitab. They're used in research quite a bit. R is open source, so you have to be, willing to learn a bit on your own with R. But all 4 of them are really good programs, very popular, and the 2 in the middle here are quite expensive. But back to our dot plot. A dot plot will actually show the data points. So you can see here's a number line here. We've got a title. We always want to have a title. We've got our horizontal axis is the only axis we've got. It's labeled. And you can see the actual data. So 45, we had, of those 70 numbers, there were 2 45s, there was a 46. So like a histogram, you can see how the data are distributed, how they're spread out. But the advantage of a dot plot, you can reclaim the actual data points. So these are all actual data points. So with a histogram, you'll see how the data are distributed, but the actual data points or the raw data cannot be seen. So the note here basically just says that one of the huge advantages of a dot plot is the raw data can be seen on a dot plot. And this phrase raw data just means the actual data. So whenever you hear raw data, you're just talking about the actual data. You didn't do anything with it. These are the actual data points in that set from problem number 16. One last thing we should probably talk about are line breaks. Just so if you see these in the book, you'll know what they're doing. So they'll do something like this. There's a couple ways to see these. So let's say you've got a vertical axis, we've got a horizontal axis, maybe a number line, and you'll see this little break in the data. And then this will start at like 60, maybe 70, 80. This just represents a break in the data because you want these to be consistently spaced because you're trying to convey information. So you want them consistently spaced, but you don't really want to start at 0 and have a giant gap before there's any data seen, right? So you don't necessarily, let's say your smallest data point is 62. You don't really want to start, going 10, 20, 30, 40, 50, 60. And then you have all this space here that's just wasted. So this line break just means there's part of the number line missing. So that's the way that our book typically does it. Another way you'll see them done is something like this, where you have a line like this, and then it continues on. Same thing. It means the same thing. It just means part of the number line is missing here. Okay, one thing we should probably take a look at is number 12 in the book. So this is in the homework section, page 54 and 55. And let's take a look. It says, the following histograms are based on different random samples of size 100 drawn from the same population. So all three of these are drawn from the same population. Now if you notice what we've got the frequency here. It's a histogram. We've got a number line here. And you'll notice that the way they set this one up is they're using the midpoints. So they're using the midpoints for this number line, right? So here's a data point of 0, 1, 2, 3, 4. So they're not using the endpoints over here. They're using the actual midpoints. So part A says, identify the midpoint of the class with the highest frequency in each of the three histograms. So class, remember the class is just like the little, each one of these bars is basically a class of numbers. Like this particular class of numbers has a midpoint of 4. So identify the midpoint of the class with the highest frequency in each of the three histograms. So in the first histogram here, this is the tallest one, right? This is the tallest one. So the midpoint of this class is 5, right? Identify the midpoint of the class with the highest frequency in each of the three histograms. So in the first histogram, 5 is the midpoint of the class with the highest frequency, right? It's the highest frequency. What about this one? What do you think? 4, right? 4 is the midpoint of this class, and that class has the highest frequency. And finally, this one has a midpoint of, if you look at how this is going, be 0, 2, 4, 6, 8, right? So it's 2. So 2 is the midpoint of the class with the highest frequency. Then it says, using the class midpoints, what is the range of data shown in each histogram? So range of data. Right now, we are going to use the everyday language for the word range, like when somebody says, well, the numbers range from 10 to 25. Now later, in chapter 3, we're going to define this. We're going to use a mathematical definition of range. But for now, it's just everyday usage. So using the class midpoints again. Remember the midpoints, that's just how these histograms are set up. Using the class midpoints, what is the range of data shown in each histogram? So this first histogram, using the midpoints, the range of the data is from 0 to 17, right? This would be 14, 15, 16, 17. So this first one, using the midpoints, the data range from 0 to 17. This one would be from, what? 1 to 16. And this last one would go from 0 to 28. Right, so I just wanted to do this one so we make sure we understand how to read these. It says, which of the histograms are more clearly skewed right? Well, remember, we were talking about shapes of histograms. I said that very rarely are they perfectly shaped. Very rarely are they perfectly skewed right or perfectly mound shaped symmetric. So this one's saying which are more clearly skewed right. Remember, skewed right means tail on the right. You can sort of see that all of them have somewhat of a right skew, right? It has a little bit of a tail on the right. But they're asking us which of the histograms are more clearly skewed right. So probably this one. Now we are sort of answering this with an intuitive approach. I mean, there's a ways to measure skewness. We just don't cover that. So we're just looking at it and thinking which one seems to be more clearly skewed right. So looking at this one is definitely, I would say, more clearly skewed right. This one has maybe somewhat of a right skew. I'm not sure if this one really has too much of a right skew, but this one is definitely more clearly skewed right, this third graph. Then it says, based on your study of random samples in Chapter 1, is it surprising to see the variations in the samples as displayed in the histograms? The original population from which the samples were drawn is skewed right with a high frequency near 4. Do all three random samples seem to reflect these properties equally well? Well, no. I mean, we would expect some variation, right? Even though each of these three samples came from the same population, there's just going to be random variation in the samples, right? So they don't reflect these equally well. So the population has a high frequency near 4. Well, it sort of is near 4. This one is at 4. This one's sort of near 4. And so the population, let's see, the original population is skewed right. So, you know, they're gonna vary. They are different samples. So they're not gonna reflect these properties equally well. Okay, so hopefully that will get you started. 2.1 is a little bit of a smaller section because we're not doing these histograms by hand. We just have to be able to read them. So go ahead and give it a shot. And of course, if you have any questions at all, just let me know.